What if the night over a sleeping city were a map of the universe? 100 billion windows flicker like distant stars, each one hinting at plans, at futures not yet drawn. In a corner office, a few bright minds sketch new streets, erase old lines, and imagine what could be. Now widen the frame to a galaxy. What if a handful of extraordinary stars do the very same there? Steering gas, carving paths, deciding where tomorrow's suns will rise. Come with me as we meet these cosmic architects. When we gaze out into the cosmos, we see galaxies as majestic, serene islands of stars. We see the graceful, swirling arms of a spiral, or the smooth, ethereal glow of an elliptical. But beneath this calm exterior lies a dynamic and often violent process of creation and change, a story that is only now being fully revealed. For centuries, we believed stars were merely passive residents of these vast cosmic cities, their positions and fates dictated solely by the galaxy's immense gravitational pull. We saw them as points of light, not as engines of change, but that perception has been shattered. Thanks to the unprecedented power of the James Webb Space Telescope, whose infrared vision can pierce through the obscuring veils of cosmic dust, new images have confirmed a startling reality. Giant star clusters can actually reshape the very galaxies they are born in. These are not just any stars. They are colossal congregations of stellar behemoths. These stellar powerhouses are not just inhabitants. They are active sculptors of galactic architecture, wielding forces that can be felt across thousands of light years. To understand this cosmic influence, scientists conducted a landmark study, a cosmic census of epic proportions. They analyzed nearly 9,000 young star clusters across a host of 30 nearby galaxies. Among them were famous cosmic neighbors like Messier 83, the southern pinwheel galaxy, a beautiful barred spiral about 15 million light-years away, and the stunning NGC 628, also known as the Phantom Galaxy, located around 32 million light-years from Earth. These galaxies, with their active star-forming regions, provided perfect laboratories for observation, allowing astronomers to witness this galactic remodeling in action. Within these stellar nurseries, they found the engines of this galactic transformation. Massive newborn stars, some weighing up to 50 times more than our own sun, and shining with the light of millions of suns combined. These are the O-type and B-type stars, cosmic titans that burn hot, blue, and incredibly bright, but live fast and die young. The regions studied are packed with thousands of these stellar giants, all blasting unimaginable amounts of energy into the surrounding space, a collective effort that dwarfs the output of individual stars. This process, known as stellar feedback, is a relentless, multi-pronged assault on the galaxy's raw materials. First, there is the intense ultraviolet radiation, which ionizes the surrounding hydrogen gas, hitting it to thousands of degrees and causing it to expand. Then come the powerful stellar winds, streams of charged particles flowing from the stars at millions of kilometers per hour. Finally, after just a few million years, the most massive of these stars end their lives in cataclysmic supernova explosions, unleashing shockwaves that thunder through the cosmos. These three forces all work together, pushing gas and dust across vast cosmic distances. It's a constant, energetic outflow that reshapes the interstellar medium. Over millions of years, a timescale that is but a blink of an eye in the life of a galaxy, this constant pressure carves out gigantic cosmic bubbles, some stretching thousands of light years wide. Imagine a bubble so vast that light itself would take millennia to cross it. These expanding cavities fundamentally alter the galaxy's structure, clearing out entire regions of the gas and dust needed for star formation, while compressing that same material in others, like a cosmic snowplow. This feedback has a profound dual effect, acting as both a creator and a destroyer. On one hand, it can trigger a fresh wave of star birth along the compressed edges of the bubbles, where the gas becomes dense enough for gravity to take over and collapse into new protostars. But on the other hand, it can completely halt star formation by blowing away the necessary raw materials, creating vast, empty voids within the galactic disk. Over time, this delicate balance between suppression and stimulation changes how galaxies evolve and dictates where future generations of stars can form. This is where the James Webb Telescope truly shines. Its infrared eyes pierce through the dusty cocoons that shroud stellar nurseries, revealing newborn clusters still wrapped in the gas of their birth cloud. In these images, we can see the process happening in real time. The combined light and winds from the young stars punch hot cavities into the surrounding material, leaving behind crisp, glowing bubble rims that trace the shock front across the galaxy's spiral arms. In galaxies like Messier 83 and NGC 628, these glowing rims are not just beautiful features. They are active construction sites. They trace precisely where the stellar feedback has compressed the interstellar gas to its breaking point. Along these dense filamentary edges, gravity bites harder, overcoming the outward pressure, and in these compressed knots of material, a second generation of stars begins to spark, born from the ashes of their older, more massive siblings. To confirm this, astronomers meticulously compare Webb's high-resolution infrared images with maps of different gas types, like the warm atomic hydrogen and the cold, dense molecular clouds where stars are born. The correlation is undeniable. Where stellar feedback has cleared out material, the maps show a deficit of cold gas, and star formation stalls. But where the feedback has piled up that material at the bubble's edge, the maps show dense concentrations of molecular gas, and Webb's images reveal brilliant knots of new star formation. This observational evidence is now being fed into powerful supercomputer simulations, which can model the physics of galactic evolution over millions of years. These simulations now reproduce the expanding bubbles, the formation of vast chimneys that vent hot gas out of the galactic plane, and the great fountains of energy that rain back down onto the disk. The remarkable match between these theoretical models and the real-world observations from Webb confirms that stellar feedback is a master architect of galactic design. The message is profound, and its implications stretch all the way down to the scale of individual planets. Star clusters don't just live inside galaxies. They actively steer their evolution. By shaping the flow of gas today, they decide where tomorrow's suns and their planetary systems can form. This process enriches the galaxy with heavy elements forged inside massive stars and scattered by supernovae, the very elements needed to build rocky planets and, perhaps, life itself. The same violent forces that clear out vast regions of space also deliver the building blocks for new worlds. These stellar architects are not just shaping galaxies, they are setting the stage for the emergence of suns, planets, and maybe, just maybe, life